In this video, we're going to talk about momentum and impulse. So momentum is defined as an object's mass times its velocity. So we give momentum the variable p. I'm not sure why, but it's given the variable p, lowercase p, and that's equal to mass times velocity. Okay, so its units, as you may can guess, are the units of mass times velocity, or kilogram times a meter per second. And as you can see, because velocity is a vector, momentum is also a vector. It's a vector quantity, and it has the same direction as the velocity. So same direction as velocity. And momentum actually shows up in Newton's second law. So Newton's second law, F equals ma, is not exactly the way Newton wrote it. So the first way you learn it, it's actually a special case. So Newton's law, second law, said the sum of the forces, or the net force, is equal to, he actually said it's equal to the change in momentum over the change in time. Okay, but if we substitute our equation up here, this is the change in mass times velocity over the change in time. But our mass typically doesn't change. So mass doesn't change. So this delta really doesn't affect it. So we can write this as just mass times the change in velocity over the change in time. But the change in velocity over the change in time, this is just the acceleration. So this is how we get Newton's second law that we see when we cover forces. And it's really a special case of Newton's second law when the mass doesn't change. And we're still not going to look at cases where mass changes, but now we're going to look a little bit closer at momentum and how it can help us solve problems. So momentum, because it is a vector, it can be broken into both x and y components, okay, just like any other vector. And so if we have the x and y components of momentum, we can find the magnitude of momentum using Pythagorean theorem. We can find the direction of the momentum using inverse tangent. Okay, so you should really think of momentum as a vector just like you would velocity and force in any other vector. So we've seen a conservation law with work and energy, namely the conservation of energy. We also get a conservation law for momentum. So conservation of momentum. And this says that if there is no net external forces, so no net external force on a system, then the momentum for that system is conserved. So if this comes directly from Newton's second law, the sum of the forces is equal to the change in momentum over the change in time. If this equals 0, so if the net force equals 0, then that must mean that the momentum is not changing. So the change in momentum is 0. So P is not changing with time. So it must be constant. Since momentum is a vector, this means that the change in momentum in the x direction, or px final minus px initial, must also be 0. Or this says the final momentum in the x direction is equal to the initial momentum in the x direction. And we get the same thing for the y direction. So py final minus py initial must be 0. or the final y component of momentum must equal the initial y component of momentum. Okay? So the momentum is conserved in both directions. So why do we use momentum? Well, it's useful for solving problems where objects, specifically multiple objects, interact or collide. So when you have things colliding like billiard balls, so maybe before you have a system of two objects, so two, say, billiard balls, and they're going toward each other, and then after they kind of collide and bounce off each other, now they're going different directions. Okay, so here they were getting closer and closer, and then eventually they hit each other. Okay, and we know when they hit each other, they're changing their direction, so there must be some force accelerating them. But these forces, these collisions, happen over such a short amount of time. Okay, so these interactions or forces, force would be another word for an interaction, so or forces, are exerted on each other. They occur so quickly. So these interactions or forces exerted on each other occur so quickly and may change, so they may vary over the course of the collision. So when they first collide, maybe they're not pushing on each other very hard, but when they, as they kind of get closer to each other, the forces increase, and then as they move apart, they decrease. Okay, so the forces occur very quickly and they may change. And so that makes it really hard to use Newton's laws for objects that are colliding like this. Okay, so instead we can look at the total momentum of the system. So for total momentum, we use capital P, and since momentum is conserved, we write capital final momentum is equal to the total initial momentum of the system. So we use capital P when referring to the momentum of the entire system. And so our entire system would be the momentum of block 1, so P1F plus P2F, and these are lowercase, since it's just a single object, is equal to P1 initial plus P2 initial. Okay, so the total final momentum of our system is the total final momentum of each block, and the total initial momentum of the system is the sum of the momenta, the initial momenta of each individual mass. Okay, so we said that momentum is a vector, so we can break it into components. So we're going to run into a problem where we're going to get a lot of subscripts. So if we look at our conservation of energy for our total system, it starts off simple, but then we have an x direction where we have Pfx is equal to Pix. Okay, and then the total final momentum, well, we have P1 final in the x direction plus P2 final in the x direction is equal to P1 initial in the x direction plus P2 initial in the x direction. Okay, so it's really, and we get the same thing for y. Okay, so I won't write it again, but you can see we have three subscripts. We have one that tells us which object we're talking about. We have another that tells us whether or not it's final or initial, and then we have a third subscript telling us which direction. So you really need to be careful and really organized when using momentum to solve problems, and especially in 2 dimensions, because these subscripts kind of get a little bit confusing. Okay, but they're a way for you to organize everything. If you didn't have them, it would be really hard to tell what you were talking about. So everything on this side is final. Everything on this side is initial. So everything on the left should have an F, and everything on the right should have an I. And then what I like to do is I like to just worry with my X component all at once. And so I know everything in this equation should have an X in it. And then if I'm talking about the total momentum, then that means I need to do it for all of my objects. So I should have one term on this side for object 1, one term for object 2. Okay, so I should have a 1, a 2 on this side, and I should have a 1 and a 2 on the other side. Okay, so sometimes students end up putting everything for object 1 on the left and everything for object 2 on the right, and they split it up, but you really have to be careful. When you move things around, it may end up being that way, but you really have to focus on setting your final quantities equal to your initial quantities, and then just go from there, being very organized. Okay. We said that momentum was useful in talking about interactions and collisions between 2 objects. So we want to look at 2 different types of collisions. Okay, the first is called elastic collisions. And elastic collisions occur when kinetic energy is conserved. Okay, so this is when objects completely bounce off each other and they don't lose kinetic energy to heat or sound or anything like that, which really isn't practical. It's kind of an ideal case. An example is, a good example is billiard balls. So we'll forget that they make a lot of sound. But when they bounce off, they don't deform or anything like that. They kind of bounce off and go in the opposite directions. And they don't lose a whole lot of energy. Okay, they still may be moving pretty quickly after the collision. The other type of collision is inelastic. Okay, and so in this collision, kinetic energy is not conserved. So kinetic energy is not conserved, or it's lost. And so it might be lost to heat, it might be lost to sound. Another common way is deformation. So if you imagine shooting a bullet into a block of wood, the block of wood is going to be deformed after the bullet collides with it. It's going to leave a hole, and in making that hole, you had to use some of your energy. Okay, so deformation is a common way that you lose energy in a collision. Okay, and so for an elastic collision, if it's completely inelastic, this means that the objects stick together. Okay. So when they stick together, this is the maximum amount of interaction they can have. And then if kinetic energy is not conserved, but the objects don't stick together, then these are just partially elastic, partially inelastic. Okay. So we don't call collisions completely elastic. They're either elastic or they're inelastic. And they may be partially inelastic if they don't stick together. They may be completely inelastic if they do stick together. Okay? And both of these types of collisions are based on the fact that energy is either conserved or not conserved. But what about momentum? Momentum is always conserved. Okay? And this is why we want to look at momentum. Okay, because it doesn't matter what type of collision or interaction happens between our objects, we know that momentum is always going to be conserved, and so we can use conservation of momentum in order to solve these problems where it would otherwise be very difficult. So let's look at completely inelastic collisions, because we can use the fact that our objects stick together to simplify some of our equations. Okay, so this is when the objects stick together after the collision. Okay, so the final momentum is equal to the initial momentum. So this means I take the final momentum of the first object plus the final momentum of the second object equals the initial momentum of the first object plus the initial momentum of the second object. Okay. Then I can plug in my formula for momentum, and this is I'm going to be able to rewrite this as the mass of the first object times the final velocity of the first object, and so on for the second object. Mass 1 V1 initial plus mass 2 V2 initial. So again, be careful with your subscripts. Your mass isn't going to change, so it doesn't get an I and an F. You just have to indicate which mass you're talking about. But since the objects stick together, that means their final velocity is going to be the same because they're going to be moving together at the end. So V1F and V2F are the same or equal if the objects stick together. So instead, we're just going to call this VF. There's no final velocities on the initial side, or there shouldn't be. And so the only final velocities are going to occur here, and they're equal, so we're just going to replace it with VF. So that means we get M1 VF plus M2 VF, and we only have subscripts on our initial quantities. And so now we can factor out this final velocity. And we have a slightly simpler expression. So if we want to solve for our final velocity of objects in a completely inelastic collision, we can just divide by this sum of the masses, and we get M1 V1 initial plus M2 V2 initial all over the total mass M1 plus M2. Okay, so this is a way to sort of simplify, because you don't have two final velocities, you only have one to worry about since they stick together. Okay, now we'll look at elastic collisions. Specifically, we'll look at a special case. Okay, so in this case, kinetic energy is conserved for elastic collisions. So this means that we can use our conservation of energy equations. When we talked about work and energy, we can use these equations for the two objects in our system, or multiple objects in our system, and the conservation of momentum equations. Okay, and then we're going to look at the special case when our second object starts from rest. Okay, so I'm not going to do the derivations, but if you use these equations for this special case where the second object starts from rest, then you can get some equations. So we're going to call this object A and object B. So mass A and mass B. Mass A is going toward mass B, and they're going to collide, and the velocity, so the velocity of object B initially is going to be 0. Okay. So in this case, you can derive an equation for the final velocity of each object. So the final velocity of A after the collision is going to be mass A minus mass B, and you don't have to worry about where these come from, over the sum of the masses times the initial velocity of A. And then for the velocity of object B after the collision, you get twice the mass of A over the sum of the masses times the initial velocity of A. So these are equations that you can use. So you can use these when the collision is completely elastic. So we don't call it completely elastic, but when it's an elastic collision, so what I mean by completely is we know for a fact kinetic energy is conserved, and when the second object, so in this case we called it object B, is at rest before the collision. Okay? So in this case, so you have an object that's just going toward a second object that's not moving, you can immediately go and look at these equations, and if you know their masses and the initial velocity of object A, you can get the final velocities of both object A and B. So this is sort of a shortcut that you get by using the fact that kinetic energy is also conserved. And we'll use these equations in an example problem. Okay, so you can see exactly when we would want to use these, and they're just useful to remember, or you may be given them on some formula sheet when you're solving problems. Next thing I want to talk about is impulse. So, impulse, we're going to start with Newton's second law. So, force is change in momentum over change in time. If we rearrange this for the change in momentum, this is going to be our force times some interval of time. We're going to give this quantity, the force times this time interval, we're going to define this as the impulse of this force. And it's going to be given the letter capital J. Okay? And because force is a vector, impulse is also going to be a vector. Okay? So the units of impulse are going to be kilograms times meters per second, or it's going to be a Newton times a second. So if you look here, a force times a time is a Newton times a second, but it also has units of momentum, or kilogram times meter per second, mass times velocity. Okay? So we say that an impulse of a force is equal to the force times the time interval over which the force was acting. So over which the force was applied. Okay? So our definition of impulse is force times this time interval, but we notice it is also equal to the change in momentum. So change in momentum of the object that the force was acting on. Okay? Before and after. Okay? So like momentum and like force, it is a vector, so it has components just like force and momentum, and so we can have a Jx and a Jy. So it's important, don't get this confused with joules. If you have a J as a quantity, a physical quantity in an equation, then it represents impulse. If you have J as a unit of a quantity, that unit would be joules. Okay, so don't get that confused. In a collision, your forces may vary. Okay, we said this earlier. We're talking about collision. So if you look at the force over time during a collision, it may shoot up rapidly and then fall off rapidly. So this would be our force versus time. The peak would be our maximum force that was experienced. And then the collision occurred from some initial time to some final time. Okay. And this is the area under the curve. This area under this force versus time curve represents the impulse. Okay, so it has units of force times time. Okay, but this shape may be difficult to take the area of, especially if you don't know the force as a function of time and if you don't have calculus. So to remedy that, we can replace this force curve with an average force. Okay, so if we have this force that varies very sharply from some Ti to Tf, if we just find the average force, we can replace it. We can replace this force curve with just an average force and pretend this average force is acting over the full time interval rather than this force that's changing all the time. And this area should equal the area under our force versus time curve that we had before. So however much we're missing in this region, we're making up for over here on the sides. Okay? So we can replace with an average force, and now it's really easy to find the area under this curve, because now the area is just the length times the width of this box or this rectangle. The height of this box is going to be our average force, and the width of it is just Tf minus Ti, or our time interval. And this equals the impulse. Okay, so sometimes your force as a function of time may be given by a curve, and so we could use this curve to find the impulse in this way. Okay, and we'll see equations where this is useful, and we'll go through some practice problems using both momentum, conservation of momentum, and impulse in a later video.